Why does your roof exist? It sounds like a silly question. You see it every day. It keeps out the rain, blocks the sun, and that's it. You've never thought much beyond that. But what if I told you that the very thing you overlook every day could be generating electricity? No batteries, no solar panels, no complicated devices. Just heat, sunlight hitting it during the day, cold pulling away at night, and a few very ordinary materials. Sounds implausible, right? And that's exactly the point. Because this isn't new. It's been known for a very long time. It's not something just invented. It's not future technology. It's always been there, right in front of us. But almost no one talks about it. Not because it doesn't work, but perhaps because we've never really looked at it the right way. So the question is, if it's this simple, why have you never heard of it? To understand this, we have to go back to 1821, when a physicist named Thomas Seebeck conducted a very simple experiment. One so simple you could replicate it at home. He took two different metals, joined them into a closed loop, and simply heated one end. No battery, no chemicals, nothing activated in the way you might imagine. Just heat. And then something happened. A compass placed nearby started to deflect, as if an electric current was flowing through, and there really was. Not because of any chemical reaction, but simply because the two different metals responded differently to temperature. That was all. Two materials, a small temperature difference, and nature did the rest. That effect is now called the Seebeck effect. It sounds grand, but its essence is extremely simple to the point that it's easy to overlook. And that's exactly what most people have done. Once you understand that principle, that just two different metals and a bit of temperature difference are enough to generate electricity, the next step becomes almost obvious. Those conditions exist right on your roof. Think of a metal roof on a farm in the American Midwest, or a wooden cabin in Colorado. During the day, sunlight pours down, heating the roof surface to 60 or 70 degrees Celsius, 140s, 158 degrees far. You can feel that heat clearly if you touch it. But when the sun sets, heat begins to radiate away into space, and by midnight, that roof can cool down quickly, sometimes approaching the surrounding ambient temperature. This means that every day nature naturally creates a clear temperature cycle without any equipment needed. And if you recall what we just discussed, that temperature difference is exactly what generates electric current. In the early 20th century, before the electrical grid reached everywhere, especially in rural areas of Europe and North America, some people recognized this. They didn't need to call it the Seebeck effect. They simply noticed that if you connected two different metals, for example copper and iron, and placed one end in a hot spot and the other in a cool spot, you could measure a small current. And so they started using it. Simple metal strips were attached to roofs or placed near heat-absorbing surfaces. No motors, no fuel, no moving parts. The system didn't need to be turned on, and it didn't need to be turned off. It worked whenever there was a temperature difference. During the day, the sun heated one end. At night, cold air or the night sky cooled the other end. Nature handled the entire process. On some farms, this system was used to provide power for very basic needs, low-power lighting, measuring instruments, or other simple applications. It wasn't a large power source, but it was enough to be useful in places without grid electricity. Imagine living in an isolated cabin, dozens of miles from the nearest power source. No generator, no modern batteries, but you could still have a small, steady source of electricity just from your roof and the natural daily temperature changes. What was remarkable was that the system required almost no maintenance. Once installed, it kept working without fuel, without constant monitoring. This made it especially suitable for rural life, where everything needed to be simple, durable, and reliable. It also fit perfectly with the American DIY spirit, using available materials, understanding basic principles, and building a working solution yourself. There was nothing complicated here. No software, no control systems, just materials, heat, and the basic laws of physics. You weren't creating energy in the usual sense. You were simply allowing energy to flow in the way nature was already prepared to do. And for a period of time, solutions like this really existed, quietly, on farms, in small workshops, in remote cabins, not on a large scale, not in cities, but in places where people tended to observe and experiment more. But as the electrical grid began to expand, as electricity became a convenient utility you could simply plug into, these simple systems gradually fell out of use, not because they stopped working, but because they were no longer the most convenient option. And over time, the idea that your roof could generate electricity just from heat and temperature differences slowly faded from everyday thinking. Not because it was wrong, but because we stopped paying attention to it. To understand more clearly what's really happening on that roof, we need to look a little deeper into the nature of this phenomenon. But don't worry, I won't drag you into long equations. Think of it simply like this. In every metallic material, there are electrons-charged particles moving freely, like people walking around in a crowded room. Normally, when everything is at the same temperature, that movement is random. No clear direction, no net flow. But when you create a temperature difference, one end hot, one end cold, everything starts to change. At the hot end, electrons gain more energy. They move faster, more chaotically, like an excited crowd. At the cold end, they're slower, with less energy. And what happens naturally is electrons from the hot region begin to diffuse toward the cold region. Not because anyone is controlling it, but because that's how nature balances energy. You can picture this like opening a door between a hot room and a cold room. Air will naturally move from hot to cold to equalize. That's the concept of a gradient of difference that creates flow. In this case, a temperature gradient creates electron flow. And when electrons move in a directed way, we call that electric current. But here's the key point. If you use only one metal, this effect is almost negligible, because within the same material, electrons at both ends tend to balance in the same way. There's no big enough difference to produce a stable current. That's why you need two different metals. Each metal has its own way of holding and responding to electrons. When you join two metals together, you create a system where electrons sense a difference, not just in temperature, but also in the nature of the material. And it's this double difference, temperature and material, that produces a measurable current. When one end of the metal pair is heated, electrons in that metal become more energetic and tend to move toward the other metal, where the energy conditions are different. When the other end is colder, that difference is maintained, and the electron flow continues. What's remarkable is that there's no engine here, no gears turning, no chemical reaction consuming material. Nothing is burned. Heat simply changes how electrons are distributed and move. An electric current appears as a natural consequence of that imbalance. You don't have to force it to happen. You just have to set up the conditions. And this is the part I always find fascinating. We tend to think of electricity as something that needs to be produced by complex machines, power plants, turbines, generators. But here, there's nothing like that. Nothing is produced in the usual sense. Instead, you're tapping into a process that already exists, thermal energy moving from hot to cold, and in the process, dragging electrons along. The current is just a sign of that process. If you reframe your perspective, you'll see this isn't technology in the way we usually think of it. This is basic physics happening right in front of us. Just like water flows from high to low, or air moves from high pressure to low pressure. No one had to invent those things. They happen because the laws of nature require them to. The Seebeck effect is the same. When you place two different metals in an environment with a temperature difference, you're not creating electricity. You're just allowing a flow that was already possible to actually happen. And if you think about it, that makes the whole story much more interesting, because it means electricity, at least in this case, isn't something rare or complicated. It's a natural consequence of very common conditions, heat and difference. And if those conditions exist on your roof every day, then in a sense, that electricity has always been there too. The only question is whether you choose to see it. If you're wondering whether all of this is just an interesting lab experiment from 1821, the answer is no. This isn't an isolated phenomenon, nor is it some vague, unproven idea. Right after Thomas Seebeck published his results, other scientists across Europe began doing what science does best. They replicated it. They took different metals, created similar closed circuits, applied temperature differences, and observed what happened. And the results were always the same. The compass deflected, current appeared, not sometimes, not under rare special conditions, but repeatedly, with astonishing reliability. That's when this phenomenon stopped being an individual discovery and became part of shared scientific knowledge. It was named the Seebeck effect. Not to make it sound more complicated, but simply to give us a consistent name for a very specific phenomenon. A temperature difference across two different metals generating electricity. And from then on, it became part of the foundation of physics. Not on the fringe, not somewhere in unaccepted theories, but right at the center of how we understand energy and matter. If you open any physics textbook on electricity and heat, you'll find this effect presented as a basic example. It's usually taught alongside concepts like current, voltage, and heat transfer, things that physics students, electrical engineers, and even high school students are introduced to. There's nothing mysterious here, nothing hidden in secret documents. In fact, it's taught openly, repeatedly, across generations. And it doesn't stop at theory. The Seebeck effect is also used in many real-world technologies you may not even realize. Temperature sensors, thermocouples rely directly on this principle to measure temperature in industrial settings, engines, and even household appliances. And space exploration, where batteries or conventional fuels are limited, thermoelectric generators have been used to convert heat from radioactive sources into electrical power for probes. That shows this isn't just a nice theoretical idea. It's a practical, reliable tool that's been used in the harshest environments. And the important point here is, no one in the scientific community doubts the existence of this effect. It's not an untested hypothesis. It's not a fringe theory that only a few people believe in. It's standard physics, verified, taught, and applied. When you look at it that way, you start to realize we're not talking about something strange or mysterious. We're talking about a fundamental phenomenon that's been well understood for over 200 years. And that makes the original question even more intriguing. If this is common knowledge, if it's taught in schools and used in industry, then why do we so rarely think about applying it in simpler ways, like right on our own roofs? And when you put all of this together, a fundamental physical phenomenon, verified for over 2 centuries, the next step becomes almost unavoidable. Looking at your own living environment and realizing that the conditions for this phenomenon to occur are right there in front of you. Let's go back to your roof one more time. Not as a built structure, but as a surface that directly interacts with energy from the sun and the night sky. On a typical summer day in the United States, whether you're in Texas, California, or even the Midwest, a roof, especially a metal one or a dark-colored one, can easily reach 60 to 70 degrees Celsius, 148 degrees Fahrenheit, under direct sunlight. You don't need a measuring device to know this. Just touch it, and you'll feel it. It's hot enough that you can't keep your hand there for long. But then the sun sets. The main energy source disappears, and at the same time another process begins. The roof starts losing heat. It radiates heat to the surrounding air and, more importantly, directly to the night sky, a giant heat sink with a very low effective temperature. As a result, the roof temperature drops quickly. By midnight or early morning, the same surface that was scorching hot during the day can become cool, close to ambient temperature, or even lower under certain conditions. That means every day-night cycle, your roof experiences a significant temperature change, often tens of degrees Celsius, without any intervention from you. No switch, no control system, no operating cost, just the rotation of the earth and the flow of energy from the sun. And if you recall the principle we discussed, this is exactly the condition the Seebeck effect needs, a temperature difference. One end hot, one end cold. If you place 2 different metals in those 2 temperature zones, for example, one contact point directly on the hot roof during the day and another point in a cooler area, like in the shade or where air circulates, then you created a complete experiment, not in a lab, but right on your house. The interesting thing is, you don't have to create these conditions. They already exist. You just have to recognize them. Every roof, in that sense, is a continuously operating thermodynamic system. It absorbs energy, stores it, and releases it in cycles. And in the process, it creates thermal gradients, the very thing physics needs to generate electric current. This doesn't depend on exactly where you live. Of course, the degree of temperature difference may vary between Arizona and Oregon, between summer and winter, but the basic phenomenon remains the same: hotter days than nights. And wherever that difference exists, the physical principle we're talking about can be applied. This makes it an almost universal phenomenon, not just in one country, not just under one special condition, but in most environments where people live. And this is the point I find worth thinking about. We often look for energy solutions in distant places, big power plants, complex technologies, while right above our heads every day, a simple energy conversion process is taking place that almost no one notices, not because it's hidden, but because it's too familiar. It happens every day, so we stop seeing it. But if you look again, with the eyes of someone who's curious, you'll realize your roof isn't just a passive structure. It's part of a natural energy system that's constantly operating, a system you can observe, understand, and if you want, even tap into. And then, at some point in history, the way we approached energy began to change, not because physical phenomena like this disappeared, but because a different, more convenient system began to form and spread. In the late 19th and early 20th centuries, along with the growth of industry and urbanization, the electrical grid started to emerge. At first, these were just small systems serving limited areas, but very quickly they expanded, connecting cities and then rural regions. The idea was very simple but powerful. Instead of each person generating their own electricity, a central source would produce electricity on a large scale and distribute it to every household through wires. This completely changed the way people thought about electricity. Electricity was no longer something you had to understand in order to create. It became a utility just like running water. You didn't need to know how it was made. You just flipped the switch and the light came on. That was a huge step forward in convenience. And for that system to work efficiently, there needed to be a way to measure how much electricity each person used. That's when electric meters appeared. These devices recorded consumption, and from there, bills were calculated. You used how much, you paid how much. This was a very rational economic model. It allowed companies to invest in infrastructure, power plants, transmission lines, substations, and recover costs by providing electricity as a continuous service. Over time, this system became more and more sophisticated and reliable. In the United States, especially after World War II, rural electrification brought electricity to nearly every household. Places that once had to rely on makeshift solutions like small generators or simple heat-based systems could now access a stable, powerful source of electricity simply by connecting to the grid. And when you have a reliable source that can power everything from lights to refrigerators, washing machines, and air conditioners, those small, distributed solutions, however interesting from a physics standpoint, became less appealing. Not because they didn't work, but because they couldn't compete in terms of power output and convenience. This was a systemic shift. There wasn't a single moment when people decided to overlook other methods. Instead, step by step, as the grid expanded and became widespread, people naturally shifted to using it. If you were a rural family in the 1930s or 1940s, and you were offered a stable source of electricity that could run multiple appliances at once, you would choose it. No need to think too hard. No need to build or maintain your own system. You just connected and used it. And over time, that led to a deeper change. We became dependent on this system, not in a negative sense, but in a practical one. Modern life, especially in the United States, is built around the assumption that electricity is always available. From lighting systems to household appliances to the internet and information infrastructure, everything relies on a centralized, continuously operating power grid. And when such a system becomes the standard, other approaches, simpler, more distributed, gradually fall out of view. Not because someone deliberately eliminated them, but because they no longer fit the way the new system operates. The centralized system had clear advantages, economies of scale, the ability to deliver large amounts of power, and convenience for the user. But at the same time, it also changed our relationship with energy. Instead of something you could observe and interact with directly, like heat on your roof, electricity became something abstract, coming from the outlet. You no longer saw the process of creating it. You only saw the result. And when that happened, simple phenomena like generating electricity from temperature differences didn't disappear from the physical world, but they disappeared from our everyday awareness. This isn't a story about something being hidden. It's a story about how a new, more efficient system in many ways gradually replaced old ways and in the process made us pay less attention to other options that still always existed. But let's pause for a moment and really think about this more seriously. If everything we've just said is true, if you have a simple, verifiable physical phenomenon that's been known for over 200 years and was even used in real life, then why isn't it a familiar part of how we think about energy today? Why, when you think about generating electricity, do you think of complex systems, optimized solar panels, massive power plants, grids spanning hundreds of miles instead of heat on your roof? This isn't a critical question. I'm not saying someone decided to eliminate a simple idea. What I'm doing is asking a question that science always loves. What makes an idea get attention, and what makes it get overlooked? Look at the contrast. On one side, you have a phenomenon you can explain in a few sentences. Two different metals, a temperature difference, electrons start moving, and you have current. No moving parts, no fuel, no control systems. On the other side, you have the modern energy system. Fuel is burned or energy is harnessed. Heat is created. Turbines spin. Turbines turn generators. Electricity is stepped up, transmitted through lines, stepped down, and finally reaches the outlet in your home. If you drew those two systems on a board, one would take a few lines. The other could take a whole page. And the interesting thing is, in ordinary thinking, we tend to believe that the more complex system is more real, more powerful, and therefore more correct. But physics doesn't work that way. Physics doesn't care whether a system is complex or not. It only cares whether the laws are satisfied. And in this case, that simple phenomenon fully complies with the basic laws. It's not an inferior version of a big system. It's just a different way of manifesting the same principle. Energy moving from higher to lower levels. So why don't we think about it? Part of the answer may lie in how we build and use technology. Systems like the electrical grid are designed to provide stable, predictable power at large scale. They have to meet the demands of millions of people at the same time. To do that, they must be tightly controlled, optimized, and operated to very specific standards. In that context, a phenomenon that depends on natural variations, day-night temperature changes, weather, materials becomes hard to integrate. It's not something you can easily turn on when you need it, or turn off when you don't. It doesn't follow your schedule. It follows the Earth's schedule. And that makes it less compatible with a centralized system where everything needs to be precisely coordinated. But that doesn't mean it has no value. It just means it doesn't fit certain goals. If you're trying to power a city, you won't rely on roofs to do it. But if you're thinking about smaller, more distributed applications where simplicity and self-operation are advantages, the picture starts to change. And this is where the question becomes more interesting. Not why don't we use it everywhere, but why do we so rarely think about using it anywhere? Because that's no longer a question about engineering. It's a question about perception. We live in a world where energy is packaged, distributed, and consumed in very specific ways. You don't see electricity. You only see its results. And when something becomes invisible in that way, you also stop thinking about other ways it could be created. This happens in many fields, not just energy. When one solution becomes dominant, it doesn't just replace others in reality. It also replaces them in our imagination. We stop questioning other possibilities, not because they don't exist, but because they no longer fall within the familiar range of thought. And that's what I want you to notice. It's not that there's a hidden solution, but that there are things so simple, so familiar, that we fail to recognize their value. And when you start looking at the world that way, you might wonder, how many other phenomena, just as simple, are also happening right in front of us that we never stop to think about? If you keep digging in that direction, you'll realize the answer doesn't lie in physics. Here is quite clear, but in the way we organize and exchange energy in society. In other words, in economics, electricity in the modern world isn't just a natural phenomenon, it's a commodity. And like any commodity, for it to be sold, it needs to be measured, controlled, and predictable. You need to know who's using how much, at what time, so you can calculate costs and build a stable supply system. That's why electric meters exist. That's why the entire electrical infrastructure is designed around accurately measuring the flow of energy through each household. But think about what happens when you try to apply that same logic to a simple thermoelectric system on a roof. The current generated depends on temperature differences, something that changes constantly with weather, time of day, geographic location, even the color and material of the roof. No two roofs are exactly alike. No 2 days produce the same conditions. That makes predicting output difficult. And if you can't predict, you also can't easily standardize. When you can't standardize, you can't easily build a large-scale commercial system around it. An energy company can't say, we will provide you with a system that generates exactly X kilowatts per day, because that system depends on factors beyond their control. In contrast, look at a power plant or even a modern solar system. A power plant can adjust output by controlling fuel or turbine speed. A solar panel system, while still dependent on sunlight, has been designed with standardized panels, inverters, storage systems, and fairly accurate output prediction models based on weather data. It can be packaged as a product, installed via standard procedures, warranted, maintained, and sold as a complete solution. This creates an ecosystem: panel manufacturers, inverter manufacturers, installation companies, maintenance services, financing, insurance. Every part of that ecosystem can be optimized, scaled, and most importantly, monetized. Now go back to the simple thermoelectric system. You have two metals, a temperature difference, and a small current. There aren't many components to optimize. There aren't many add-ons to sell. You don't need software to control it. You don't need a team of technicians for regular maintenance. Once installed, it mostly just exists and works when conditions allow. From an economic perspective, that's not an attractive model. Not because it isn't useful, but because it doesn't generate much exchange value in a market system. It's hard for a company to build a big business around something users can install themselves at low cost and without ongoing support. This isn't an ethical issue. There's nothing wrong with a company seeking scalable, profitable solutions. That's how markets work. Resources, time, money, research tend to flow toward places where profit and growth can be generated. And solutions like centralized grids or modern solar fit that model. They can be standardized, mass-produced, installed procedurally, and integrated into larger systems. Meanwhile, a solution dependent on the specific natural conditions of each roof with relatively low output is hard to fit into the same logic. Power output is also a key factor. A simple metal pair produces a small voltage enough to measure, enough for very small applications, but not enough to run an entire modern home. You can connect multiple pairs to increase voltage, but even then, total power is limited by the temperature difference and material efficiency. This makes it suitable for specific applications: small lighting, sensors, backup power, but not as a comprehensive replacement for the grid. And when a technology can't meet the market's main demand, providing large, stable energy, it gets less attention, less investment, and therefore appears less in everyday life. If you look at the whole picture, you see a fairly consistent logic. It's not a collective decision to overlook a simple solution. Instead, there's an economic system that prioritizes solutions that can be scaled, standardized, and integrated. Solutions that fit those criteria get developed, promoted, and widespread. Solutions that don't fit even if they still work exist on the margins, used in specific contexts, but not at the center of the system. This doesn't make them less interesting scientifically. On the contrary, it makes them more interesting, because they show that the physical world isn't limited by how we organize our economy. The laws of nature keep working the same way, whether we build a business model around them or not. And when you realize that, you start looking at everything differently. You start to see that there are possibilities that exist not because they fit the market, but because they fit nature. And sometimes, just recognizing that is enough to change the way you think about energy. If you look a little broader, you'll see that we're talking about two very different ways of thinking about energy, not just technology, but the organization of the entire system. One side is the centralized model. Energy is generated in a few large places, tightly controlled, then distributed to millions of people through a complex network. The other side is the distributed model. Energy is generated at many small points, right where it's used, based on readily available natural conditions. Neither model is right or wrong in an absolute sense. Each addresses a different type of problem, and each has very clear strengths. The centralized system, the grid you use every day, has one extremely important advantage: stability. It can deliver large amounts of continuous, near uninterrupted energy. You can turn on lights at midnight, run the air conditioner at noon, charge devices whenever you want, and expect electricity to always be there. To achieve that, the system must be designed with many layers of control. Power plants adjust output. Substations balance loads. Backup systems ensure no interruptions during failures. All of that creates an extremely complex but also very robust network. It allows modern society to operate at large scale. Without it, cities like New York, Los Angeles, or Chicago couldn't function the way we're used to. But that very centralization also comes with another feature: dependence. When you're fully connected to a central system, you rely on it for nearly every daily activity. If the system works well, you don't have to think about it anymore. But if there's a problem, a storm, a technical failure, or any disruption, you immediately feel the shortage. This isn't a weakness in a negative sense. It's a natural consequence of optimizing for scale and efficiency. Now, look at the other side: distributed systems, like what we're talking about with the thermoelectric effect. These systems usually aren't powerful in the sense of delivering large amounts of power. They can't replace the entire grid, but they have a different advantage: independence. When you have an on-site energy source, even a small one, you're not completely dependent on an external system. You can have basic lighting, maintain some small devices, even when the grid is down. In environments like remote cabins, research stations, or places where grid connection is difficult or expensive, this becomes very important, not because it provides a lot of energy, but because it provides a degree of autonomy. And this is where the difference between the two models becomes clearer. One model is optimized for stability and scale. The other is optimized for simplicity and independence. One side lets you run an entire city. The other can help you light a room in a specific situation. If you try to compare them as direct competitors, you miss the main point. They're not really competing on the same criteria. They exist at two different levels of need. And when you look at it that way, you start to see that the question isn't which is better, but which fits which circumstance. A centralized system makes sense when you need to supply energy to millions of people with high stability. A distributed system becomes sensible when you need flexibility, self-operation, or simply a solution that works in conditions where large systems can't easily reach. The interesting thing is that in recent years, we started to see combinations of both models. Rooftop solar, home battery storage, microgrids all are examples of how we're bringing distributed elements into what was originally a centralized system, not to completely replace it, but to supplement it. This reflects a more balanced approach, leveraging the power of the large system while retaining some flexibility at the small scale. And in that context, phenomena like the Seebeck effect start to become interesting again, not as a comprehensive replacement, but as part of a bigger picture, a way to understand that energy doesn't just come from big sources, but also from small, continuous processes happening all around us. When you look at it this way, you no longer have to pick sides. You don't have to say one system is good and the other is bad. You just have to recognize that each system is a different way of working with the same set of physical laws. And what matters is understanding the limitations and capabilities of each approach. A centralized system brings convenience and power. A distributed system brings simplicity and independence. And between those two poles, there's a lot of space to explore, experiment, and combine. This, to me, is the most interesting part of science, not finding a single answer, but understanding the entire space of possibilities. The Seebeck effect still exists, exactly as it existed in 1821, and long before that, from the moment there was matter, heat, and temperature differences. Electrons still move from hot to cold. Metals still respond differently to heat. The processes we've just talked about are still happening right now on your roof, on the surface of roads, on any surface exposed to sunlight and the night sky. Nothing has changed at the natural level. What has changed is us. More specifically, what has changed is what we pay attention to. When a phenomenon is no longer at the center of the system we use every day, it gradually slips out of awareness, not because we decide to forget it, but because we no longer have a practical reason to think about it. Think about other things in life that follow the same pattern. You probably learned about friction in school, a very basic concept. You understand that every motion is resisted by it. But in everyday life, you rarely stop and think, friction is at work here. It still exists, still affects every motion, but it's not in your constant awareness. Or think about atmospheric pressure. You're living under a column of air weighing tons, pressing down on every square meter of your body. But you don't feel it, and you don't think about it unless you're a physicist, or you're working in a special environment. Those phenomena don't disappear. They just become invisible because they're too familiar, or because they're not necessary for your daily decisions. The effect we're talking about is similar. It's not a secret. It's not hidden. It's taught in schools, used in industry, recorded in textbooks, but it's not part of how we interact with energy in everyday life, and so it becomes part of the background, something you learn, then set aside. This leads to an interesting misunderstanding. When something is no longer in regular awareness, we tend to feel like it doesn't exist. Not in a logical sense, but in a psychological one. If you don't see anyone using a method, you might assume it doesn't work, or that it's been completely replaced. But in this case, that's not true. The method still works. It's just not widely used in the current context. And this is the point I want you to pause and think about. The difference between doesn't exist and isn't noticed. In science, those two things are completely different. A phenomenon doesn't need human attention to exist. It doesn't depend on whether we think about it or not. It simply obeys the laws of nature. And if those laws don't change, then the phenomenon doesn't change either. The universe is still doing it, whether you look or not. This has an interesting consequence. It means there may be a lot of processes around you. Simple, continuous, reliable processes that you never notice, simply because they're not packaged into a technology you're familiar with. They don't have a brand. They don't have a user interface. They don't have advertising. They just happen. And because they happen quietly, they're easy to overlook. When you start looking at the world this way, you may see that the story of energy isn't just about what we build, but also about what we choose to see. We build large, complex systems, and they become the center of attention. But at the same time, there are smaller, simpler systems that aren't integrated into that structure, and so they exist on the edge of awareness. Not because they're inferior physically, but because they don't fit the way we organize the world. And when you realize that, you start to have a different perspective. You no longer think a phenomenon needs to be new or popular to have value. You can go back to ideas that have existed for a long time and look at them with fresh eyes, not to replace what's already there, but to understand that the full picture is always broader than what we usually see. And in this case, that picture includes those small, quiet electric currents generated every day by temperature differences, a process that nature is still carrying out continuously without needing our attention. How much electricity can such a system really generate? The answer, as is usual in physics, is it depends. But we can give some typical numbers to get a clearer sense. When you join two different metals together and create a temperature difference between the two ends, the voltage produced is proportional to that difference. This proportionality coefficient is called the Seebeck coefficient, and for many common metal pairs, it's in the range of a few microvolts per degree C. That sounds very small, and it is. For example, if you have a metal pair with a coefficient of about 40 microvolts per degree Ca, typical number for some combinations, and you create a 50 degrees Celsius temperature difference between the ends, you'll get about 2 millivolts of voltage. That's a very small number compared to a regular AA battery at about 1.5 volts. But this is just a single pair. In practice, people often connect many pairs together in series, called a thermopile, to add up the voltage. If you connect 100 such pairs, you could get around 200 millivolts under the same thermal conditions. If you scale up to 500 or 1,000 pairs, you start getting closer to a voltage usable directly for some small applications. The important thing to understand is that voltage increases with the number of pairs, while power depends on both voltage and current in turn depends on many other factors, like the material's resistance and the system's arrangement. Now let's go back to the roof. Suppose you have a metal roof reaching 65 degrees Celsius during the day, and the underside or a cooled area stays around 25 degrees Celsius. That's a 40 degrees Celsius difference. With an average Seebeck coefficient, you might expect a few millivolts per metal pair. If you build an array with a few hundred pairs, you could achieve a voltage in the range of 1 to 1 volt, depending on the materials and actual conditions. This isn't a large number, but it's enough for specific tasks. For example, industrial temperature sensors, thermocouples, often operate in very small voltage ranges and still provide accurate information. Ultra-low power electronics, like some environmental sensors or energy-efficient microcontroller circuits, can run on small power sources if paired with appropriate voltage-boosting circuitry. You could also use this energy to slowly charge a capacitor or small battery, accumulating energy over time and then using it when needed. The key is to set realistic expectations. This isn't a system that can supply kilowatts to run an air conditioner or electric stove. The power output of a simple thermoelectric system on a roof typically falls in the milliwatt to a few watts range under optimal conditions, and usually lower in reality. This depends heavily on temperature difference, surface area, thermal contact quality, and material efficiency. The conversion efficiency of traditional thermoelectric systems is also relatively low, often just a few percent, because most of the thermal energy isn't converted to electricity but continues to pass through the material. That doesn't mean the system is useless. It just means it's suited for specific applications. If you have a device that needs a few milliwatts to operate continuously outdoor sensor, a remote monitoring system, then a small but steady power source can be very useful. If you're in a place without grid power, a small source to light an LED or slowly charge a device can make a significant difference. And because this system runs on natural cycles, hot days, cold nights, it can provide power in a repeatable way without fuel. What's noteworthy is that all these numbers aren't far-fetched theory. They've been measured in labs, in industry, and in real applications. You can find commercial thermoelectric modules, small devices containing dozens or hundreds of metal pairs, for sale on the market. When placed in a sufficient temperature difference, you can measure voltages and currents consistent with these estimates. Nothing here goes beyond known physics. No numbers are exaggerated. And that's exactly what makes it reliable. When you look at the data this way, you start to see more clearly the role of this system. It's not a comprehensive replacement for large energy sources. It's a way to tap into the small, continuous energy flows that already exist in your surroundings. It operates within certain limits, and if you understand those limits, you can use it effectively. And that, in a sense, is the essence of applied science. Not looking for a solution to every problem, but understanding exactly what each tool can do and using it in the right place. So how do you turn a small effect into something more useful? The answer, in this case, isn't find a new phenomenon, but expand the one that already exists. One metal pair produces a few millivolts, that's true, but there's no rule saying you can only use one pair. You can connect many pairs together. And this is where things start to get a little more interesting, but still very simple in principle. When you connect metal pairs in series, that is, the output of one pair connects to the input of the next, the voltages add up. No need to overcomplicate it. Imagine you have many small batteries, each producing a very low voltage. If you connect them in series, the total voltage increases. Exactly the same idea applies here. Each metal pair is a small power source, and when you stack them in a chain, you build a larger power source. If one pair produces 2 millivolts, then 100 pairs could produce around 200 millivolts. 500 pairs could approach 1 volt. This isn't magic, just addition. The important thing is to keep each pair experiencing a similar temperature difference, so they contribute evenly to the total voltage. In practice, this is done by arranging the metal pairs so that one side always contacts the hot source, for example, the roof surface under sunlight, while the other side is kept cooler, perhaps by circulating air, shade, or a heat sink surface. When you look at a commercial thermoelectric module, you'll see exactly this structure. Dozens or hundreds of small metal pairs arranged alternately, connected in series, forming a single block. But you don't need to buy such a module to understand the principle. You can imagine stringing segments of metal wire in a chain, each segment acting as a pair, and all contributing to the total voltage. This also helps you understand an important point. Voltage increases when connected in series, but current doesn't automatically increase in the same way. Current depends on the total system resistance and the ability to maintain the temperature difference. When you add more pairs, you also increase total resistance, which can limit current. So scaling the system isn't just add as many as possible, but finding a reasonable balance between the number of pairs, temperature difference, and how you use the energy. For example, if your goal is to light a small LED, you need a minimum voltage for the LED to operate, usually around 2 volts for a white LED. That means you need enough pairs to reach that voltage, or you need electronic circuitry to step up the voltage. If you only have a few dozen pairs and the total voltage is just a few hundred millivolts, you might not have enough to run the LED directly, but you could accumulate energy in a capacitor and discharge it periodically. This is how many low-power systems work, not providing high continuous power, but accumulating gradually and using it when sufficient. A more understandable analogy is water. A single drop of water doesn't do much, but if you have many drops and you collect them, you can create a flow strong enough to do something. Turn a small wheel, for instance. Each metal pair is a drop of energy, and connecting them is how you gather those drops into a larger stream. But just like water, if the pipe is too narrow or too long, the flow gets restricted. That's why the physical design of the system wire length, materials, heat dissipation is just as important as the number of pairs. This brings us back to a familiar point. This isn't a magical system where you can simply multiply infinitely to get any power you want. It obeys very clear physical limits. But within those limits, you can adjust and optimize to achieve results suited to specific needs. If you need a small but steady power source, you can design an array with just the right number of pairs, arranged sensibly to maintain temperature difference, and use that energy in an appropriate way. And what's remarkable is that all of this still keeps the original spirit. Nothing complicated in principle. You don't need a power plant. You don't need a large control system. You're just expanding a simple phenomenon by repeating it many times. This, in a sense, is how a lot of technology works. Not by discovering a new law, but by applying an old law in a smarter way. When you look at the system that way as a way to gather small energy flows together, you start to see more clearly where it really makes sense in practice, not at large scale. Not to replace an entire home's electrical system, but in small specific applications where a modest amount of electricity is enough to make a difference. Let's start with the simplest example, lighting. An LED consumes very little power compared to traditional lights. With a few volts and a small current, you can already produce enough light to see in the dark. If you have a well-designed thermoelectric system with enough metal pairs and stable temperature difference, you could maintain a power source sufficient to light an LED under certain conditions, especially when combined with energy storage in a capacitor or small battery. This might not replace your main lighting system, but in a cabin, a shed, or an outdoor area, it could be a simple and reliable solution. Another application many people are interested in is charging personal devices, like phones. Here, you need to set realistic expectations. A modern smartphone requires relatively high power for fast charging, often from a few watts to tens of watts. A simple thermoelectric system on a roof is unlikely to provide that level of power directly. But if you change the approach, not fast charging, but slow charging and accumulation, then the picture changes. You could use this small power source to gradually charge a reserve battery throughout the day and night. Then use that battery to charge your phone when needed. This is how many low-power systems operate, not delivering a large amount of energy instantly, but accumulating it over time. In emergency situations, this can be very useful. Imagine a storm knocks out the grid for several days. You have no power from the outlet, but your roof still heats up during the day and cools at night. A thermoelectric system, even a small one, continues generating energy throughout that time. It might not be enough to run a refrigerator or air conditioner, but it could be enough to keep an LED light running, charge a communication device, or power a radio. In those situations, a small but independent power source can matter far more than a large one that isn't available. This is also why such systems are often considered in off-grid scenarios, places without grid connection, or where that connection is impractical. Remote cabins, observation stations, long-term outdoor equipment all are environments where you can't easily bring or maintain a large power source. There, a system that operates on readily available natural conditions, temperature, sunlight, environment becomes very appealing. Not because it's powerful, but because it's durable and self-operating. But the important thing is not to confuse capability with expectation. This isn't a free, unlimited solution that can replace everything. It has very clear limits on power and efficiency. If you expect to run your entire house just from roof temperature differences, you'll be disappointed. But if you see it as a supplementary energy source, a way to tap into the small energy flows you usually overlook, then it starts to make sense. And this is the point I think is most important. The value of this system isn't in competing with large energy sources, but in expanding the way you think about energy. It shows you that energy doesn't only come from obvious places, power plants, solar panels, but also from small, continuous processes happening all around you. And when you start recognizing those processes, you can find new ways to use them. Not to replace what's already there, but to supplement it. To add another layer of flexibility and independence to your energy system. Science, at its most basic level, isn't about reading and believing, it's about observing and testing. And the interesting thing here is that you don't need any complicated equipment to do it. You can start with very simple things. Almost everything you need is already around you. First, you need two different metals. One common and easy to find choice is copper and iron. A piece of copper core electrical wire combined with a piece of steel wire or an iron nail is enough to get started. What matters isn't perfect shape, but the difference between the two materials. Next, you create a simple closed circuit. Join the two metals together at one end. That's the first junction. Then join them again at the other end. That's the second junction. Now you have a basic system with two junctions, and these 2 points are where everything happens. One junction would be the hot point, the other the cold point. You don't need to do this in a complicated way. One point can be placed on a hot surface, for example, a metal sheet under sunlight, a cup of hot water, or any safe warm surface. The other point is kept cooler in the shade, near airflow, or in contact with something colder. What's important is a clear temperature difference between these 2 points. It doesn't need to be extreme, just enough to create a gradient. When that happens, electrons start moving, and a small voltage appears in your circuit. To see it, you'll need a voltage meter. A simple multimeter is sufficient. Set it to DC voltage mode, then touch the 2 probes to the appropriate points in the circuit. If everything is set up correctly, you'll see a small voltage value appear, usually a few millivolts. That number may be very small, but it's direct proof that the system is working. No battery, no external power source, just heat and materials. This is the important moment, because you're seeing a physical law come to life right in front of you. From here, you can start experimenting further. Increase the heat at the hot point, and you'll see the voltage rise. Cool the cold point more, and the voltage increases too. Change the type of metal, and the results will change. This isn't an on or off phenomenon. It's a continuous system where you can observe the relationship between cause and effect. If you want to take it a step further, you can create multiple metal pairs and connect them in series. The principle is very similar to connecting multiple small batteries together. Each pair generates a small voltage, and when connected in series, those voltages add up. This allows you to increase the total voltage to a more usable level. However, you also need to understand the current doesn't increase in the same simple way. When you add more pairs, the system's resistance also increases, which can limit the current. So scaling isn't just add more. It's finding a balance between the number of pairs and the thermal conditions. There are a few practical factors you should pay attention to. First is thermal contact. If the hot point isn't really hot, or the cold point isn't cool enough, the difference will be small and the voltage low. Second is electrical contact. The connections need to be secure and clean. If the connection is poor, you might measure nothing, even though the phenomenon is still happening. Third is expectations. This isn't a system that generates a lot of energy in a simple configuration. If you see a few millivolts, That's a completely normal result. The goal of this experiment isn't to produce large power, but to prove the principle. When you see the voltage appear, you know this is real. For safety, keep everything basic. You're working with heat, so avoid direct contact with hot surfaces. Use safe heat sources, hot water, sunlight, or warm surfaces. And that's enough. No need for big flames or dangerous equipment. Make sure your workspace is dry and stable, especially when using measuring devices. Finally, and perhaps most importantly, try it yourself. Not because someone asked you to, but because there's real value in seeing a phenomenon with your own eyes. When you measure that voltage, even if it's small, you no longer think of it as an abstract idea. It becomes part of your experience. And once you have that experience, the way you look at your roof, sunlight, and even the concept of energy will change a little. Once you've tried it yourself and seen the system work, the next question almost naturally arises. How do you improve it to turn a small signal into a more useful energy source? This is when we talk about optimization, not in the sense of turning it into a giant machine, but making better use of what physics allows. The most important factor always comes back to the core, temperature difference. The voltage you generate depends directly on the difference between the hot point and the cold point. So if you can increase that gap, you'll see clear results immediately. In practice, this often means making the hot junction hotter and the cold junction cooler, while keeping the two regions from mixing heat with each other. For example, if you placed a system on a roof, you want one part in direct contact with the most heat-absorbing surface like a metal roof under sunlight, while the other part is isolated or well dissipated to stay lower. This leads to the second factor, placement. Not every spot on the roof is the same. Areas that receive direct sunlight for many hours will generate higher temperatures, while areas with good airflow will help cool more effectively. A good design often takes advantage of both, one side facing the sun to maximize heat, and one side facing cooler air, or attached to a heat sink to maintain the difference. You can think of this like putting one end of the system in summer and the other in spring at the same time. Next is materials. Not all metals are the same in terms of the Seebeck effect. Some material pairs produce higher voltage for the same temperature difference. In real applications, people use special materials like bismuth telluride designed to optimize thermoelectric performance. However, these materials can be more expensive or harder to access, so in many cases, you have to balance performance and availability. Copper and iron are easy to find, cheap, and good enough to prove the principle. But if you want to optimize, choosing the right materials can make a significant difference. Another factor often overlooked is heat loss. If heat from the hot junction easily spreads to the cold junction, you lose the temperature difference and with it, the voltage. So thermal insulation between the two regions is very important. You want to keep the heat flow going through the system, not around it. This can be achieved with insulating materials, reasonable spacing, or simply ensuring the two junctions aren't too close without separation. At the same time, you also want to optimize heat dissipation on the cold side. A large metal surface with good air contact can help pull heat away faster, keeping the cold junction truly cooler. When you start thinking about all these factors, temperature, placement, materials, insulation, you'll see that optimization isn't a single step, but a process of balancing many small elements. Each improvement may only bring a small change, but when combined, they can create a significant difference in overall performance. However, and this is the important point, all these improvements still stay within certain physical limits. You can't overcome those limits just with design. The efficiency of thermoelectric systems is limited by how thermal and electrical energy interact in materials. Even with the best materials, only a fraction of the thermal energy is converted to electricity. The rest continues to pass through as heat. This means you can't expect such a system to achieve high efficiency like other technologies designed specifically for large-scale energy production. And that's completely normal. Every technology has its own sweet spot. In this case, that spot is small applications where simplicity, reliability, and self-operation matter more than maximum efficiency. When you understand these limits clearly, you can design the system more realistically. You don't try to turn it into something it isn't. You focus on making it work best within its range. And that, in a sense, reflects a broader principle in science and engineering. Optimization isn't about overcoming nature, but working with it. You observe what nature provides: heat, difference, materials, and arrange them in the most effective way. You don't force the system, you guide it. And when you do that right, you'll see that even a simple phenomenon can become much more useful than you initially thought. When you put all those principles and optimizations into a real-world context, you start to see more clearly how the system is used in life, not in a lab, but in very specific situations. Imagine a small cabin in the Colorado mountains, or a wooden house deep in the forest of Montana, places with no direct grid connection, or where running power lines is too expensive compared to the usage needs. The owners of such places usually aren't looking for a perfect system. They're looking for one that works well enough, is reliable, and requires little maintenance. In a typical case, an off-grid resident might combine several small energy sources: a small solar panel for daytime, a storage battery to hold energy, and a simple thermoelectric system to take advantage of the day-night temperature difference. The thermoelectric system here isn't the main source. It's a supplementary one, a small but continuous energy flow. For example, during the day, the cabin's metal roof heats up under sunlight, while the underside, or a heat dissipating surface, stays cooler. Metal pairs attached between these two regions generate a small voltage. At night, as the roof cools faster than the surrounding air, the thermal gradient may reverse or maintain in a different way, but still produces some difference. The result is that the system doesn't produce a large amount of electricity at any one time, but it operates on natural cycles, day after day. The cost to build such a system is usually quite low, especially if using readily available materials like copper and steel, along with some basic components like wires and measuring devices. Compared to installing a large energy system, this is a much simpler and more accessible solution. This fits the philosophy of many off-grid people: reduce dependence on external infrastructure, make use of what's available, and accept reasonable limits. In terms of performance, the results are often very realistic. You don't have a powerful source. You have a small, stable source under suitable conditions. It may be enough to slowly charge a reserve battery, maintain a few low-power devices, or provide basic lighting. In some cases, the system is used to power environmental sensors measuring temperature, humidity, or monitoring surrounding conditions devices that need very little power but must operate continuously for long periods. What's important is that the system doesn't require frequent intervention. Once properly installed, it keeps working without fuel, without daily adjustments. This makes it especially suitable for places where regular maintenance is difficult. The stability here isn't high-power stability, but existential stability. It's still there, still working, as long as natural conditions exist. However, it's important not to exaggerate what this system can do. In real examples, no one relies entirely on thermoelectricity to run their whole life. It doesn't replace other energy sources, it supplements them. An off-grid cabin usually still needs solar panels, or even a small generator for bigger needs. The thermoelectric system only contributes a small part to the total energy, but that part can be valuable in specific moments, especially when other sources aren't performing optimally. When you look at cases like this, you start to see the real role of this technology. It's not a forgotten miracle solution, but a simple tool suited to certain circumstances. It works well when expectations are realistic, when the design fits the environment, and when it's used as part of a larger system. And perhaps the most interesting thing is that the people who use it often don't see it as special technology. For them, it's just another way to make use of what nature already provides: heat during the day, cold at night, and turn it into something useful. No hype, no big promises. Just a small, steady solution in a world where sometimes small things like that are exactly what you need. When looking at real examples like this, the most important thing isn't to exaggerate the system's potential, but to set the right expectations about its role. This isn't a replacement for the grid, and it never will be in the modern context. You won't run an air conditioner, washing machine, or an entire house just from roof temperature differences. The grid exists for a very clear reason. It provides large, stable, predictable energy that meets the demands of millions of people at once. Nothing in a simple thermoelectric system can compete directly with that. But that doesn't make it meaningless. On the contrary, it becomes useful precisely because it doesn't try to replace the whole system. Its value lies in the gap situations where a small, independent, self-operating energy source can make a difference. As a backup solution, it can play a role when other systems fail. In a power outage, when everything that depends on the outlet suddenly stops, a small power source that keeps going can become far more valuable than when everything is normal. It may not provide much, but it provides something important: continuity. You still have basic light. You can still keep a small device running. You still have a certain level of control in an uncertain situation. Beyond practical value, this system has another value that's often overlooked: educational value. When you build or observe such a system, you're not just using energy. You understand it. You see directly the connection between heat and electricity, between the environment and energy flow. This is completely different from just plugging a device into an outlet. There, energy is invisible. Here, it becomes tangible, observable, measurable, and that changes the way you think about the world. You start to realize that energy isn't something that comes from somewhere far away, but is part of the environment around you. This leads to another aspect: self-reliance, but at a light and practical level. Not complete independence from every system that's neither necessary nor realistic in most cases, but the ability to understand and use a small portion of energy in your own way. You're no longer entirely dependent on a single source. You have an extra layer of flexibility, and that layer, even if small, can bring a greater sense of control and deeper understanding. However, for this system to truly make sense, you have to keep a balanced perspective. If you expect too much, you'll be disappointed. If you ignore it completely, you'll miss an opportunity to understand and utilize an interesting natural phenomenon. The point lies in the middle. See it as a supplementary tool, a way to tap into the small energy flows you usually don't notice. And when you do that, you start to see that its value isn't in replacing what's already there, but in expanding the way you interact with energy. It doesn't change the entire system, but it changes the way you look at that system. And sometimes a change in perspective is the most important thing. When you expand your view to the entire energy picture, you start to see that what we're talking about isn't just a small phenomenon on your roof, but part of a larger trend, the way we're gradually rethinking energy for the future. For many decades, the centralized model has dominated, and it will continue to play a major role. But alongside that, a shift is happening, from fully centralized systems toward more flexible, more distributed ones. You can see this in the growth of rooftop solar, home battery storage, microgrids, and many other technologies that allow energy to be generated and used right on site. This isn't complete replacement. It's supplementation, a way to make the overall system more flexible and resilient. In that context, phenomena like the thermoelectric effect, even though small, fit naturally with the idea of decentralization. They don't require large infrastructure, don't need complex connections, and can exist independently at many different points. Every roof, every heat-exposed surface, every environment with a temperature difference can become a small energy source. When you combine many small sources like that, not just thermoelectric, but also solar, wind, storage, you start building a hybrid system where each component contributes in its own way. Such a system doesn't depend entirely on a single source. When one source drops, another can compensate to some extent. This doesn't just increase flexibility, it also increases the resilience of the entire system. Sustainability here isn't just about using clean energy. It's about designing systems that adapt to natural conditions instead of fighting them. Instead of trying to create a massive energy source to meet every need, we start thinking about harnessing many small distributed sources that fit each specific environment. This also opens space for innovation, not just in inventing entirely new technologies, but in how we combine known principles. The Seebeck effect isn't new, but the way we use it can change, especially when it's integrated into modern systems with sensors, storage, and smart controls. You can imagine future homes that don't just consume energy, but continuously harvest it from many small sources around them: light, heat, motion, and manage them as a unified system. In that picture, no single source is enough on its own, but together they form a flexible and efficient energy network. And perhaps most importantly, it's a change in mindset. When you start looking at energy this way, You no longer think only about large sources. You begin noticing the small, continuous energy flows around you. You realize that energy isn't just something produced on an industrial scale. It's part of the natural environment, always in motion and always available to be tapped in many different ways. This doesn't make large systems less important, but it adds a new dimension to how we understand and use energy. And in a world searching for more sustainable, more flexible solutions, the combination of centralized and distributed systems between big technology and small phenomena like the one we've just explored may be the most sensible path forward. Looking at this entire story from far enough away, it starts to become a much bigger question than just energy or one specific physical effect. It becomes a question about how we see the world. Because if a simple, well-understood phenomenon can still exist right in front of us while almost no one notices, then that suggests an interesting possibility. How many other things are also there, but we don't recognize them? Not because they're hidden, but because they don't fit the way we're used to thinking. We tend to be drawn to complex things, big machines, new technologies, solutions that are packaged and presented clearly. And that's completely natural. Complexity often comes with scalability and power. But sometimes that very focus on complexity makes us overlook simple things, even though they're still operating according to laws just as profound. This isn't a call to turn away from modern technology. It's a reminder that simple and complex aren't opposites. They're two different ways of expressing the same reality. A power plant and a pair of metals under a temperature difference both obey the same physical laws. The difference lies in how we organize and use them. And when you realize that, you start to see that perception, the way we perceive, doesn't always fully reflect reality. Reality is still there, operating in its own way, whether we pay attention or not. But what we see, what we think is important, is shaped by habits, by systems, by what gets emphasized in daily life. This leads to an interesting consequence. There may be very basic, very common phenomena that lie outside our field of attention simply because they're not packaged into a familiar solution. And that's where curiosity becomes important. Not curiosity to find something completely new, but curiosity to look again at familiar things with a different perspective. When you ask simple questions, why does the roof heat up? What happens when it cools? What are the electrons doing in that process? You start to uncover layers of understanding you may have previously overlooked. And the interesting thing is that these questions don't require you to be a professional scientist. They only require you to pause for a moment and observe more carefully. In many cases, the boundary between the obvious and the profound is just the level of attention you give it. A phenomenon can seem ordinary until you really ask what it is, why it happens, and how it connects to other things. And when you do that long enough, you start to see that the world isn't a collection of separate things, but a network of interconnected processes. Heat, electricity, light, matter all interacting in consistent ways. The effect we've been talking about is just a small window into that network. But once you've looked through that window, you may stop wondering, how many other windows haven't we opened yet? And perhaps that's the greatest value of this story. Not a specific solution, but a reminder that reality is always richer than what we usually see. And sometimes, just changing the way you look from habit to curiosity can help you discover things that have always been there, waiting to be noticed. Perhaps the best way to end this story isn't to give a clear answer, but to return to a very familiar image or roof. It's still there, just as it always has been. During the day, it absorbs sunlight and quietly heats up. At night, it cools down, radiating heat into the vast sky above. Nothing changes in the way it operates. Nothing new is added. No technology is activated. And if you don't pay attention, you won't see anything different. But the interesting thing is that simplicity doesn't mean nothing is happening. On the contrary, it's precisely in that simplicity that the most basic processes of nature continue to occur continuously. Heat moves. Energy balances. Electrons respond to their environment. And all of that happens without our permission, without our understanding, and without us even needing to notice. Nature doesn't operate because we care about it. It operates because that's how the world is structured. And perhaps the most thought-provoking thing isn't whether we can harness all those processes, but whether we choose to see them. Because when you start really looking, the familiar starts to change. A roof no longer is just a layer of material protecting you from the weather. It becomes part of a larger energy system, a system you've always lived in, but rarely stop to recognize. That doesn't mean you have to change your way of life or abandon the modern systems we depend on. Those systems exist because they solve very real problems, and they do it very well. But at the same time, recognizing that beneath all that complexity, very simple principles are still at work can change the way you think. Not toward replacement, but toward expansion. You start to see that the world isn't only made of what's designed and built, but also of what has always existed, operating quietly. And when you realize that, you may start asking different questions. Not big questions, but smaller, more intimate ones. What's happening here that I haven't noticed? What seems ordinary but actually contains a deeper principle? Questions like that don't always lead to immediate answers, but they change the way you look. And sometimes that change in perspective is the most important thing. So the next time you look up at your roof, maybe you won't see anything different. Or maybe you'll see something new. Not because the roof has changed, but because the way you look at it has. And if that happens, then perhaps you've begun to see the world in a slightly broader way, where simple things are no longer just simple, but small doors opening to a deeper reality that's always been there, waiting to be recognized. If you feel this story has made you look at the world a little differently, please subscribe to the channel so we can explore more seemingly familiar things that hide profound laws together. I'll see you in the next video. And who knows, next time we might find something interesting again in the things you see every day.